Hello. Thank you for attending to this webinar. In this webinar, we will show the case study from a paper that was presented by Marek HANACZOWSKI on M.Sc Bridges Designer. It was presented in the Security of Bridges Congress. It was celebrated in Wroclaw last November. Roman Martin and myself, Ronald, we will be the presenters of this webinar.
This paper, you can see a capture of the paper. It was about impact on prefabricated T-type pre-stressed concrete beams. It was presented with the computational approach, finite element analysis, to reproduce an impact on a bridge superstructure according to the Eurocode. There are several aspects that should be faced in the bridge design considering this impact, and this approach was done with two different models: static linear analysis and cell elements for a global model, and then a more detailed also static linear analysis with nonlinear material models.
This software was used in this paper was CivilFEM powered by Marc. Ingesaber is the developer of this software. It's a high-end general-purpose finite element software for all type of engineering fields, including civil, mechanical, any structural sector.
Also considering the geotechnical effects, as you can see in this video. So, CivilFEM also is a object-oriented software, and it also can be part of using a friendly user interface. It can be used as with Python scripts. Marek, for this paper, created a script where here you can see the different sections modeled with these scripts with the different inputs.
Yes, you can see that you can automate processes with Python very easily for loops, if conditional statements, anything that can be automated. It can be with any type of library.
Also, the main reason of using CivilFEM for this analysis, CivilFEM powered by Marc, was the very advanced nonlinear concrete material model. It considered cracking and crushing behavior, and also it considers other nonlinear behavior of concrete like creeps, syncrates, also time-dependent material properties, and also coupled analysis like thermal structural analysis for, in example, maturing heat in early concrete, or fire analysis, or just considering the reduction of material properties.
Let's see some examples of collisions. Some of these images that you can see, these cranes or big trucks that have impact to the structural part of these bridges. Hopefully these cases are not very common, but of course they can happen. Okay. Once the structural part is impacted, you can see here the consequences of the damage. Okay.
Well, and what about the Eurocode? What does the Eurocode indicate about this type of impact? The Eurocode indicates to apply equivalent static loads. This equivalent static loads depends on the type of road, but for highways and national main roads, this force is equal to 500 kilonewtons. That is clear, but it's not very clear where and how to apply this force. You can see here different schedules of different bridges, and it's not very clear following the Eurocode where to apply these loads in horizontal with some angles and in different parts. Also for the Eurocode, it allows different analysis types, linear elastic, brittle elastic, and also for cracking, for tension behavior. In our case, we will use the multilinear, nonlinear elastic with a crack stress and a softening, following multilinear load. Also, for compression, the Eurocode also allows different loads, elastic, perfect plastic. In our case, we are using the multilinear elastic. So the computational assumptions are the following you can see here. An equivalent force, static force of 500 kilonewtons is simulated. Also, first, a linear elastic cell model of the whole bridge will be used to perform a general analysis, and then a solid model of a detailed T-beam section SWOT model to take into account all the nonlinearities, considering the nonlinear stress strain analysis adopting following the Eurocode, and also some different assumptions like the fracture functions for the bilinear chart and also for the shear retention factor to consider the fracture energy. Also, all these options can be input with CivilFEM powered by Marc, and also the reinforcing bars were modeled with trusses and inserted. Here you can see on the right the stress-strain relationships that were input in CivilFEM. The top of one is the compression parabolic law, and the bottom graph on the right is the post-cracking behavior. After cracking stress of 3.5 megapascals, there's a bilinear softening load. It can be input any type of stress-strain relationship also for fiber reinforced concrete. CivilFEM considers there's these different shear retention factor laws. This is the law that was considered for shear failure. And also, this is for tension, and also for compression, it considers the triaxial compression behavior. So with this advanced nonlinear concrete model, it was used for the second model. For the first model, this is the linear elastic model with a general, the whole bridge, and with a lateral impact.
Well, in this case, a Python script was used from the beginning, as you can see here. First, the parameters to create the geometry.
And first, the cross-section is generated. We are launching the macro, and you can see step by step with some steps where it's created. First, a cross-section is generated. This cross-section can be used to generate the longitudinal a beam in the longitudinal way, and then it is copy and transfer in the transverse direction, one single beam. Also, all this geometry is generated through different parameters. If we modify those parameters, the geometry is updated. Just consider this is only the geometry. It is not already meshed. And after generating the geometry, meshed loads and so on will be applied. The boundary conditions also will be applied at the bottom, as you can see there. And in the parameters, here is the parameters that are generated. In example, the span length. If we modify this data, the geometry is updated. So once we can create parameterized geometry with the scripts for different loops to generate repetitive structure, and we can also modify and update the structure through different parameters. So this is a very powerful tool of CivilFEM that can be used to just to create different, to update different models. Here you can see I've increased one span first and the second one, just modifying these parameters. And this is a very powerful tool for updating all models for the same bridge for different locations, or just to optimize the structure, checking different geometry. After generating the mesh and applying laws. First step is solving for self-weight to check that the model is correctly done. Just checking vertical displacement in this case, that all is connected, and in this case longitudinal deflections. Here we can see the different values and check that the bridge is well for the self-weight and all first data is correctly applied. And then next step is applying the impact of the load. Here we can see there are some of the results of the impact of the load. First we can plot stresses, and then we can select the beam where the impact was produced and check maximum and minimum stresses. For the maximum principal and minimum principal stress, we can analyze compression and tension stresses. And this is linear, elastic. These stresses are helpful for analyzing just the impact effect, but the problem is the accuracy of these linear elastic models. But it is a first step for just advancing to the non-linear, more accurate model. Well, just plotting the minimum principal stress for tension and also the maximum for compression. Here you can see the stresses due to the impact on the bottom and on top, where you can add different levels for extracting different plots. You can see there where those stresses are related. Yeah. Also,
these are clipping options for results. In this case, for one web of a T-beam, you can see here results.
So well, CivilFEM has a very friendly user interface that allows many options to obtain many plots and results and to analyze them.
These are the shear force of this model was this web was modeled with shell elements, and here you can see the shear force.
Yes, you are seeing the thickness because we are plotting the shell elements considering thickness, but it is just a plane of elements with shell elements for this web. We are not plotting the flame, and here we are plotting the shear force in these shell elements. Also, a part of plotting and adding different levels for maximum values. Also, a path could be extracted through those the section or the width of the or the height of the elements, and extract those graphs to analyze forces and moments and to extract shear forces, mainly shear forces and bending moment on the web of this T-beam.
Yes, because later we want to see the chart as it happens with beams, okay, in 2D. Here are now the bending moment.
Here we're plotting the bending moment with the maximum value on the connection between the flame and the flames and the web. And well, some results we have of this model. Here are the displacement due to the impact in millimeters. We can see the impact creates 2 millimeters, a little bit more than 2 millimeters displacement. Here we can see from the bottom view how all beams are affected. So you can see this is a precast T-beam bridge with a compression slab on top, and just plotting bending moments on the impacted beam, just in the web part. Here you can see more details and maximum values. The same for shear force, and also the previous path that we have selected. We can have for different beam types. We have selected T21, 24, and 27. Just different values for bending moment in the different axes, longitudinal, transversal, and shear force. And there you can see the shear and the bending moment path.
Yes, now you can see the nonlinear model.
This is the detailed nonlinear model, and this was meshed with solid elements, nonlinear solid elements, also the shear force, the reinforcing for shears and bending, and pre-stressing rebars. In this case, instead of generating the model using CivilFEM tools, the geometry was imported. The geometry can be imported from the different CAD models, and in this case, we have different lines for the reinforcement, and this is the cross-section that is divided in an area for the precast, prefabricated beam. We have added several points and then split for those that curvature, and on top on green you can see the compression slab that is added after. On the construction process is added that concrete part after the T-beam is placed. So CivilFEM can consider material age and different material properties for an evolutive construction analysis. If we check different material properties, first these are the properties for the pre-stress tendons, and this is we are using a nonlinear law, just bilinear stress-strain relationship for the tendons, the pre-stressing tendons. Also, these properties are defined following the Eurocode. For concrete, you can see concrete is a time-dependent material model. So, first we can plot the elasticity modulus. This is elasticity modulus, depends on the different days for the construction process. So we can add for the precast concrete certain time for considering different age of concrete and different properties, and for the compression slab on top, we can select another age for that concrete. So CivilFEM will consider different material properties for both, considering a very detailed construction process. And as we are using in this case the 28 material properties, here you can see for compression, this is the parabolic law. Instead of parabolic rectangular, we are using this much more accurate law, which is a parabolic one, the 28 one. And for compression, there are different laws to use, Bouilly-Cousous and stopic hardening. Then for cracking, we select for the different cracking options. Cracking stress could be constant, time-dependent, or age-dependent crack stress. So that is, for example, early age material properties and also for different fire analysis. And this is the post-cracking behavior. You could see the stress-strain relationship. Also, here in this case, for the post-cracking behavior, the crack stress is 3.5 megapascals and bilinear softening. For compression, the compression crashing failure is based on compression strain of 0.35%. When the compression reaches that value, failure happens in that element. And the final data is for reinforcing bars, the bilinear law, as you can see there. So you can see it's a fully nonlinear model. Also, there are contacts between top and bottom parts. You can see the green and the blue one. We have defined a contact to define that joint. That contact could be frictional only or also cohesional. And also due to the rebars that goes from the different parts, the connection considers those rebars and the joint will work with the contact behavior, frictional or cohesion frictional behavior, plus the intersection of these rebars in both concrete volumes. So these are the details of the model. Also here you can see that the rebars don't need a congruent mass for work together. There's an option of insertion, and they are working together without merging and congruent mesh. And these are the loads and the boundary conditions. You can see the impact, the 500 kilonewtons is divided in an area for applying a pressure. And what you can see, there are different plot options, but just to check the model. Well, results views, you can see here, we can plot first stressing, displacements, and many other values, as we saw.
Total displacement.
In this case, total displacement. As you saw before, we can plot maximum principal and minimum principal stress for compression and for tension stresses. In this case, well, first we have plot displacements due to the impact, and here we are plotting stresses.
The minimal.
You can see these are the compression stresses that happens in the opposite phase to the impact and in the connection between the web and the flame. That is where the maximum compression forces act. And also for checking the
cracking
tension stresses, here we can plot the minimum principal stress, and here you can see
cracking strains.
The different principal cracking, the principal tensile stress, and also the cracking. If we plot cracking strains, you can see the maximum crack happens in the connection between wave and flame. But we can modify the range because that is a huge crack, just to be able to appreciate the rest of the cracks. So modifying the range, here we can appreciate 45 diagonal cracks. We are going to reduce a little bit more the range for these values to be able to appreciate different cracks. So here you can see, due to the impact, around the impact there are 45 degrees cracks in the web, and a longitudinal crack in the connection between the web and the flame, and in the opposite side of the beam there are longitudinal vertical cracks.
You can see that the units can be changed anytime, regardless the units of the model, geometry or mesh.
Also, you can extract different videos, plots, and there are many options for post-processing. Also, you can just hide different parts of the model. In this case, we are hiding concrete, just for analyzing stresses on the rebars. Here we can see maximum von Mises stress, and we can see that even with this huge impact and the damage on concrete, we can see that the maximum stress, the von Mises stress, is below yielding stress. So there is no plasticity on these rebars due to this impact. So so this, as there is no yielding and the stress on these bars are below yielding stress, we can determine that this beam can be reinforced and could be repaired, because it is not a very high damage, only the concrete part. So here there are different options to select and to hide the different, and we can create different groups considering different reinforcing bars types, just for a really easy and fast plot option. Also, for determining the safety factor, what we did is increasing the load until the collapse of the model. Collapse happens with the non-converging of the model, when the damage generate different mechanisms, and model stop converging because of these mechanisms. So you can see here that the model stopped converging at about over 1.5, the safety factor. So this safety factor could be is as if it was determined by the Eurocode greater than 1.5, and there you can see maximum principal stress in both sizes of the bridge, and also here you can see for 1.5. It means we have applied 1.5 times the 500 kilonewtons, and you can see here maximum cracks in both sizes of the model of the beam. And here a video that was extracted with CivilFEM, and you can see how the cracks are generated during the impact
from one side and the other. Okay. Well, as a summary, just you can see that here we have two models, a linear elastic and a nonlinear model. We found that the linear analysis the results were very conservative, so we perform a nonlinear analysis. Okay. Eurocode allows the use of nonlinear analysis, describing all the failure modes, and the detailed criteria procedures for determining the load capacity, in this case 1.5, still need to be clarified. CivilFEM is a powerful and friendly and effective software, and with the help of Python scripting and the possibility of parameterization, you can create your own wizard.
Well, here the Marek presentation finished, where he remarked the Python options for creating different for improving CivilFEM with different, in this case, to generate automatically generation of different cross sections. And well, if you would like to ask something else about his webinar, you could email them, or you could email us, and you could contact us about his paper that was presented in Poland. He's Polish, Marek HANACZOWSKI, and we would like to thank him that he facilitated all this information.
But the webinar is not finished. In this case, we have performed other examples, composite bridges. Okay, in this case, an impact from one side, as you can see, of the bridge was applied. Okay.
Two different configurations, one without bracings on the right and one without bracing on the left.
Yeah, here you can see the green beams.
To improve the behavior of this composite bridge for lateral impacts.
And here you can see the comparison of one bridge with stiffeners and without stiffeners.
Also, this bridge is curved, so it increases the need of 3D models, considering these lateral loads, and the behavior of these bracings is more important, considering this curve and how these lateral impact loads are transmitted to the rest of the bridge and the effect on the other beams.
Another composite bridge, we have used another impact.
This is a box steel section with a concrete compression slab on top. Well, all these models till now were done with equivalent static loads following the Eurocode, and here we can see some other models that were performed with CivilFEM with transient analysis. This is the brittle block impact on a wall and how cracks breaks the model. This has a brittle behavior for tension, as you can see there on the right. And this is another model that was performed just with CivilFEM of a ship impact on this the steel part
tower
of the tower of a wind turbine and the effects on that. So, well, thank you very much for your attention. Also, we would like to thank Marek for all this information about his paper that we used just for this webinar. Just if you would like to have more information about the software or the examples we saw, just don't hesitate to contact us. Also, we can contact with Marek for any answer. Please, if you could complete the survey, it will be very helpful for us to improve these webinars and the information and the software that we have. And of course, if you would like to try and to check CivilFEM, you could do it, and please do not hesitate to contact us for a trial version.
Yes, the survey will be delivered when we finish the webinar, or in the mail with the recording of the video.
But if you would like more information, please email us, and we can give you more information about this.
Thank you. Bye.